In this section, we're going to look at our first redistribution case study and talk about specifically what are the problems and then what are the potential resolutions. So right now, as we have the network pre-configured, we're running OSPF on the right-hand portion of the network, we're running eHRP on the left, and then we have three different points of redistribution. Where specifically router 1 is redistributing eHRP into OSPF. We have router 3 redistributing OSPF back into eHRP. And then we have router 9 who's doing connected redistribution of its own links into the eHRP process. So first off, before we look at the actual end result of why is the loop happening, let's go ahead and do just a basic reachability test to see what is reachable currently, what is not, and from there we can make the decision of where we need to look more specifically in the network. Now we may even want to cut down, if we take a look at the previous script that we were using, we may want to cut down on the amount of information we have in that, and maybe we'll start with just the loopbacks of the routers. So let's go ahead and build a new script that is just going to be the loopbacks, and assuming that works, then we can go one step further and then test reachability between all of the interfaces. So we're going to say that we go to our TCL shell, we're going to create a for loop, we'll say for each loopback. And the loopbacks here specifically are 151.1.1, 151.2.2, and so on and so forth. So all the way up to router 10. So 4, 5, 6, 7, 8, 9, and 10. Because also part of the issue too is that once we find what the problem is, we don't want to have to cancel the script over and over and over. If we're sending packets to 50,000 destinations and 49,999 are not reachable, then we don't want to go ahead and continue to ping all of them. Once we find something that is unreachable, that's going to give us an indication of where the problem is, and then we can do some further investigation. So again, like I said, we'll do it just with this basic test, and then if this one works, then come back and do the detailed one. So we're going to ping the loopback, and then we're going to do this from everybody. So first off, let's just do a brief view of the routing table. Let's say like from router 10's perspective, and we show IP route. It is in the OSPF domain, and we can see that we have not only internal OSPF routes, but we also have external. So this at least tells us that some sort of redistribution is working, that someone is originating the prefixes, but it doesn't necessarily tell us do we have actual end-to-end reachability to it. Now again, in OSPF, when we originate an external route, there's two different ways we can originate it. Either as a type 5 LSA in normal areas or a type 7 LSA in the not so stubby areas. To figure out which one we actually have, if we were to look at the show IP OSPF database and look towards the end, we're looking at specifically either the type 5 or 7 LSA. And the important point about this is who is the advertising router, or in other words, who is doing the redistribution, who is the ASBR. So router 1 we can see is the ASBR here. Now likewise, if we were to go to the eHRP domain, let's say we take a look on router 6 and see what does it know about the rest of the OSPF network. So on router 6, let's say show IP route eHRP. And if everything is working, we should see not only our internal eHRP routes, but we should also see the externals. So let's pick one of the externals. Let's say this link here, 155.110.0. And let's look at the details. Let's say show IP eHRP topology for 155.110.0/24. And we can see that we know it's an external route, and it says that the originating router is router 3. So in other words, at least it tells us up to this point that basic redistribution was working. So we didn't forget to put the metric. We didn't forget to put the redistribute statement. We can see most of the prefixes are being installed in the table. Now, it wouldn't make sense to do the actual connectivity test unless we check at least this basic information. Because if the routes aren't there, we know we can't reach them. It's a waste of time to try to actually do the pings. So, but at this point, it looks like everything is good from just a high-level overview. So let's go ahead and try this out. And again, in my case, I'm using the chat window here under Secure CRT. So if you go to View and then go to the chat window, or just right-click up here and go to the chat window, the reason I'm using this is so I can send the commands to all the routers at once. But normally you would just go to the routers and paste this in individually. Okay, so it looks like most of the stuff we have reachability to. Some of the stuff it shows there's a little bit of packet loss. You know, maybe that's normal, maybe that's abnormal. We don't necessarily know yet. So let's do this. Okay, we can see towards the top here, maybe one packet was lost. And this could be a couple different reasons. Maybe I didn't have a MAC address for the destination over Ethernet and I had to ARP for the next hop. Or maybe it's a transient loop in the control plane. I don't really know. So it might make more sense now, since I didn't have 100% reachability to all destinations, I'm going to go ahead and increase the repeat count. Let's say instead of sending 5 packets, let's send 100. And out of those destinations that I was able to reach, let's see if we can get 100% reachability out of 100 packets. Because that's going to take a little bit more time in order to run through. And then if there is a flap in the table, I might be able to catch it in that duration. So let's say that the repeat count is now 100 packets. And we'll do this again for all the routers. So it looks like for most of them, most of the reachability is there, with the exception of 150.1.9.9, which specifically is router 9's loopback. So now we've narrowed it down a little bit in the topology where the problem exists, but we don't yet know what the problem is. So before we even look at the CLI, let's think of this from just a very high-level overview. We said there's 3 different points we're doing redistribution. We're doing on router 1 from EIGRP into OSPF, on router 3 from OSPF into EIGRP, and then on router 9 we're doing redistribute connected. Now the issue here is that we need to take them as separate cases and look at them one at a time and look at them on a hop-by-hop basis. So starting at router 9, let's think about how the other devices should be learning its prefixes and what are the links that they should be using in the routing table as the outgoing interface. So router 9 does the redistribution, and it's advertising the route out towards router 7. Now let's assume this is actually working. So we may actually want to go one step further before we look more details into the topology to see on router 9, am I actually advertising it into EIGRP? And the way that we could do this is by simply saying show IP EIGRP topology for 151.99/32. And it says that it is being advertised from redistribute connected. So we are advertising it. It is being originated. So router 9 is originating it into EIGRP. Router 7 should be seeing it as an external EIGRP route with an administrative distance of 170, and it should be reachable via router 9. So if I am correctly routing the packets from 5, 5 should be routing them that way. Now, or excuse me, router 7. If router 7 is correctly routing the packets, it should be routing it directly to 9. Okay, next router 7 is going to continue to send the advertisement on. So it sends the advertisement up to router 6, it sends the advertisement to router 3. Now at this point, since we haven't done any other redistribution yet, as the network stands now, router 6 should install the route through 7, and 3 should install the route through 7. And we should see the same exact pattern as we did on router 7, that it should be installed as an external EIGRP route with an administrative distance of 170, and from router 6's point of view, it's going to be reachable via router 7. Router 3 should do the same thing, but it's going to say that it's reachable via router 7. Then it's going to get to 1. 1 should say it's reachable via router 6. Okay, now router 1 takes the route and redistributes it into the OSPF domain. So we're taking the route that used to be an external EIGRP route with a distance of 170, and we're going from the high administrative distance to the lower one. And again, this is the typical problem case for distance-based loops. That if we go from a high protocol to a low protocol and then try to return back, we're going to prefer the lower administrative distance and then potentially route in the wrong direction. So next, let's think about how does one advertise the route. So it's going to be flooded over the DMVPN network. It goes up to the hub, which is router 5. And 5 is going to flood it out all of its interfaces. So it goes down to 8 and 10. It should go back to router 4. Router 4 is then going to reflood this on the DMVPN. But 5 is going to realize that it's the originator, so that one gets dropped. So again, OSPF, even though it will have a control plane loop of the flooding, that's the normal behavior of OSPF. That should not be an issue. Now, in other protocols like RIP or EIGRP, that will be an issue because there's distance vector. They don't know the overall topology graph. So next, router 5 continues to flood, and it's going to flood the update to router 3, and it's going to flood it to router 2. Now, at this point, router 3 is performing redistribution. We're going to take the route from OSPF and redistribute it back in to EIGRP. Assuming the origination works, router 3 is going to advertise the route to router 7. So the next thing we need to think about is, from router 3's perspective, was it actually allowed to do the redistribution or not? Well, what are the cases where we say, yes, you can redistribute it, or no, you cannot? It's not based on the routing database, remember, it's based on the RIB, based on the routing table. So the real question now becomes, when router 3 got the advertisement, it's getting it two different ways. It's getting it once through external EIGRP, and it's getting it once through OSPF external. Which one is it going to prefer? Well, we have two different protocols, but we have the same longest match. So what's the attribute that we look at then? We look at the administrative distance. So we're comparing external EIGRP, which is a distance of 170, to external OSPF, which by default is a distance of 110. So 110 gets installed in the routing table, and the EIGRP route gets flushed. This means that we can no longer advertise the route through EIGRP. So for example, if we were to say that router 2 here was connected to router 3 only with EIGRP, and if router 2 was not connected to the OSPF network, one of the issues that we would run into is that router 2 would never learn this route. Because with a distance vector-based protocol, if the route is not installed in the RIB, you can't actually advertise it to other destinations, because you can't guarantee it's loop-free. But again, OSPF and BGP are different, because OSPF already has an overall view of the graph. Even if it doesn't install the route, it can tell you, I guarantee that it is loop-free. But outside of this scope here, let's not take router 2 into account yet. We'll look at this a little bit later here with this example. But just from router 3's point of view, up to this point, we should be able to tell, just based on the way that the topology is physically laid out, that router 3 will not use the external EIGRP route, and it will install the OSPF route with a distance of 110 via router 5, via the DMVPN hub. Now, once this occurs, router 3 says it's in the RIB, which means I can now redistribute it back into EIGRP. Now, this might not necessarily be a problem case. It really depends in the EIGRP network which is going to be the preferred route. So now we have the external EIGRP that is being learned by router 3, and we have the external EIGRP that's being learned by router 9, the original originator, the one that the traffic is supposed to go to. So now let's think about who's making the decision up to this point to figure out which one's going to be advertised on. So the route is coming in this direction from 9 to 7, and it's coming in this direction from 3 to 7. 7 now has to make a decision. Well, we know that the protocol is the same, right? It's both EIGRP. Distance is the same. Assuming that we didn't change it, the external distance is 170. So now what is the attribute that we're going to look at? We're going to look at the metric, right? To figure out what is the closest advertised distance to the prefix. And then we're going to compute our entire feasibility condition to say who has the lowest end-to-end metric. Now, the value that we're actually using here is going to depend on what are the seed metrics. And let's take a look at the topology, or let's take a look at the CLI and look at specifically what are they doing in their redistribution, 9 versus 3. So on router 9, if we look at the show run section router, router 9 just says redistribute connected. Okay, nothing special. Router 3, if we show run section EIGRP, router 3 says redistribute the OSPF process into EIGRP, and we have to set some sort of metric because, again, there's not a default seed. With the connected link there was, because router 9 can say the connected link has this bandwidth, it has this delay, it has these other attributes. That's what's going to go into the topology. So we need to think about then, what was that connected link to begin with? In this case, it's a loopback, and what were the vector attributes of it? So if we look at router 9 and look at the show IP interface loopback 0, actually just show interface loopback 0, we need to know what was the bandwidth. Okay, the bandwidth was, that's 8 meg, 80 meg, 800 meg, 8 gig is the bandwidth. And the delay is 5,000 microseconds. It says the reliability is 100%, the transmit and receive load are 1, but these don't really matter because these aren't weighted by default in the EIGRP process. Now this is again assuming that we looked at the EIGRP process and we knew that these values were not weighted. If the metric weights were changed and bandwidth, load, reliability, and delay were taken into account, then we would need to look at those other attributes. But in this case, the K values are the default. So we're going to look at the minimum bandwidth plus the addition of the delays. So now let's look at this from router 7's point of view. Router 7 here is really the one that is making the decision to say, am I going to choose to route via router 9 to get to the destination, or am I going to route via router 3? If it makes the decision to 9, we know that's the correct decision, right? However, what would happen if it made the decision to 3? It would say, send the packet this way. 3 sends the packet this way. 1 sends it back into EIGRP. 6 sends it to 7, and then it loops. So before we look at the details, we know that the problem now is reachability to router 9's loopback. We can tell because there's no reachability at all. But instead of looking at the details of the routing process, let's do this now. Let's do a trace to say, how do we actually get there? What does this show? Okay, let's look at it from the start from router 10's point of view. It says we're sending the packet to 8 to 5 to 1 to 6 to 7 to 3 to 5 to 1 to 6. So there's a loop in the network. There's a loop in the data plane. The packet is going from 5 to 1 to 6 to 7 to 3. Then 3 is looping it back to 5. So here's where the loop starts. So who's making the wrong decision here? The destination is actually that way. So the issue is on router 7. Why is 7 choosing to route to 3 versus choosing to route to 9? And again, these are the type of loops that are a little bit easier to try to narrow down, because if you look at the trace route here, it's obvious there's a problem. That the packet, not only is it not getting to the destination, but it's infinitely looping until the time to live expires. So if we were to set the TTL to 255, the maximum of the packet, we would see 255 hops. But it just happens to be that the trace route default is to choose 30 hops as the TTL. If we did a trace here and then set the time to live, TTL to 255 with a maximum of 255, we would see, actually minimum would be 1. We can see it's going to loop 255 times. So normally in a real design, this is the reason why you have the time to live to begin with. That if for some reason the control plane makes a wrong decision, we want to make sure not to infinitely loop the packets. So eventually the loop will be broken, but it's broken in the data plane, it's not broken in the control plane. Okay, next let's look at some other tools. Before we look at specifically why did router 7 make the wrong decision, there's a couple different things we're going to look at. One of them is going to be, on all of the routers, we're going to look at the debug IP routing. Okay, debug IP routing is simply going to show us, are there changes happening in the routing table? So did I get a new advertisement? Did I delete an old advertisement? Did the metric change? Did the administrative distance change? This is going to be a real good indication of churning or any type of thrashing in the routing table, where I used to route out this link and now I'm choosing another one. And then I'm flapping back to the original one, back and forth. Now, if we were to let this run for a couple minutes, and we would see in this particular case, nothing is happening. There's no output. Let's make sure that we are actually logging. Let's say show log. It says on the console we're logging debugging, and that logging is enabled. If we show users, We're on the console. So we should be getting those debugs if there was a problem. Okay, let's make sure that the debugging is actually working. Let's say on router 10, let's say clear IP route star. Okay, we can see it is adding the prefixes back. And we can see flushing the routing table on one of the boxes. It does cause the rest of them to reconverge. But what we would be looking for here specifically is, does the table eventually settle down? So if we see that at some point they stop convergence, which would be our normal event, that in the internal network at some point OSPF should stop running SPF, that EIGRP should stop waiting for the query replies to come back in, the real only exception to this is BGP. The internet table never converges. You'll see that because of constant flaps, you're constantly recalculating the table. That's the normal case. But in IGP, when you look at the routing table, you want to make sure that the routes are as old as possible. That's what tells you that the table is stable. Now, if we were to look at the table, and in this case, I just cleared it recently, so the timer would be reset. But if we show IP route, and if we look at the timer and we see that the timer is something like 5 seconds, and we check it again, and then the next time it says it's 3 seconds, that would be an indication of a control plane loop, that something is changing in the routing table, either constantly refreshing the route or withdrawing and advertising the route. Then we would know where to look into more detail. But here, specifically, that's not the case. The table is stable. The table is just making the wrong decision. And that's the key difference here between a data plane loop versus a control plane loop. It's not that the route is flapping, it's just that someone made the wrong choice. And the way that we saw where that choice was made wrong is by looking at the trace and looking at where does the loop converge. So where is the central meeting point that the device is supposed to send the packet that way, but it went back into the loop that direction. And in our case specifically, it's router 7. 7 should have forwarded the packet to 9 because we know that basically simply based on how the topology looks. That no one else is connected to 9, so the packet would have to go this way to get there. So let's now look at router 7 and think about specifically why did 7 make the wrong decision. So on router 7, we're going to show IP route for that specific prefix. Show IP route for 150.199. And it says I'm learning this via router 3. Whereas we know 7 should be learning it through 9, correct? Because that's where the actual destination is. So now on router 7, how do we figure out why did it choose one over the other? Well, really the next thing we need to think about is did 7 even learn the route to 9 in both directions? And we can check this by looking at the EIGRP topology and then look at the feasibility condition. So if we now look at the show IP EIGRP topology for the prefix 150.199/32, it says that we're learning it from 2 different routers. We're learning it from router 3 and we're learning it from router 9. Now in the external data, we see that there's 2 different originators. Router 3 is an originator and router 9 is an originator. So both of them are redistributing it into the process. If we were to compare the actual path selection, what are the values here that we're looking at specifically that is causing us to choose router 3 as the best path? It's the feasible distance, right? So router 7 is saying we have 3,072 or we have 130,816. Well, this one's clearly higher, so we're going to choose that as the best route, and that's the one that gets put into the routing table as the successor. But why specifically did it choose that? Because we didn't really change anything. All I did was say redistribute connected on one side and then redistribute OSPF into EIGRP on the other side. The issue is that I seeded the metric wrong, and the metric of the loopback has a high delay by default. And we can see this here specifically in the topology. It says that the total delay via router 9 is 5,010 microseconds. The total delay via router 3 is lower. But the issue here is that based on the physical topology, there is never a valid case where router 7 should send the packet to 3 to get there. So in reality, it's not really a problem with 3 sending the wrong metric. It's that 3 shouldn't even send the route. Because if the link to router 9 goes down and 3 continues to advertise it, traffic's not going to get there because there's no other physical connection. So this is one of the issues that you need to think about is where does the route actually belong in the topology? If it's in some portion of the network that you can't ever reach, then you shouldn't be advertising it. So let's think about then what are the possible solutions? Well, one of the solutions would be just to take router 3 out of contention. If we were to go to router 7 and to verify 100% that this is the problem to begin with, let's do this. Let's just go to gig 137 and just shut the link down. If once the link is shut down, then we are able to reach router 9, we now definitely know that's the problem. And if we look at the trace, we should be tracing directly to that next hop. Okay, let's bring the link back up. Gig 137, no shut. And then let's see, can we still reach the destination? Now we can't. Let's look at what does the trace say. We're going from 3 to 5 to 1 to 6. And then it continues. This here is basically router 7 cannot send an ICMP unreachable to itself, but it shows us the rest of the looped path. This would be another good indication that 7 is the problem here, that it shows the path and then it shows that the packet's dropped, and then it shows the path again and then it shows the packet's dropped. Okay, so now we narrowed down the problem. The problem is that the metric was seeded wrong when 9 redistributed the route. So what are the potential solutions? Well, one would be that we could seed the metric lower. So on router 9, we would say when we redistribute the route, make sure that the delay is low and make sure that the bandwidth is high. So then router 7 should prefer this as the exit. But that would basically just be masking the problem. The real problem here is that router 3 should never have advertised us this destination to begin with, because it cannot be in the forwarding path other than through router 7. So it never makes sense for 7 to route through 3. That would always be a looped condition. This means that there's a number of other simpler solutions to this problem. But first, let's look at just seeding the metric. Let's see if we change the metric to be high on router 3, will that actually solve the problem? So on router 3, let's look at the show run section EHRP. And let's go to the EHRP process, and let's say that we redistribute OSPF1 in, but we're going to give it a really bad metric. So we're going to say all 1s. That's basically like not necessarily the worst possible case, but it's a very bad metric value. Now let's look at the result from router 7's point of view. If we show IP route for 151.99, it says now we're going to go to 9. If we look at this in the topology table, let's now look at the difference between the two advertisements. Router 7 says if I want to go to 9, the metric is 130,000. If I want to go to 3, it's much, much higher. So we know definitely that this is going to be excluded. We're going to choose this as the successor. That's the one that actually gets installed in the routing table. Okay, so now let's run the script again. Let's see, can we actually reach all of the destinations correctly now? Because we also want to make sure here that the change that we just made did not affect any of the other prefixes. Because again, remember, in IGP, the attribute does not belong to the route, the attribute belongs to the link. So we're changing the link level attributes, which are changing all routes. This is again different than BGP, where the attribute does belong to the route, and we could have just said for that route to 9th loopback, set the local preference higher, or set the AS path prepending out a different direction that we don't want to be the preferred path. But in IGP, this becomes much more difficult because the change that we're making, we might not realize the overall impact of it until we test reachability to all destinations. Okay, but we can see this did fix the problem. So this is one solution, is to say that when router 3 does the redistribution of EHRP, or excuse me, of OSPF into the EHRP process, set the metric as some high value. So then we would prefer the lower metric that router 9 is originating, and the packet should be able to go there. Now again, this doesn't necessarily mean that we have the optimal path though, because if we were to go to router 3 and trace the destination, router 3 is going to choose to go into the OSPF domain to get there. Because we're looking at a difference in the administrative distance. That router 3 says I have the route through OSPF, I also have the route through external EIGRP. 110 is lower than 170, so 110 gets installed. And we would see this here on router 3 if we show IP route for 151.99. This should be pointing into OSPF with a distance of 110 versus to the other neighbors. So let's do the trace, and let's say we source this from our own local loopback. So from router 3's perspective, the packets are going the long way around. It's going from 3 to 5 to 1 to 4 to 7 and 9, but maybe we don't care. It really depends on what are the individual requirements. The requirements may be just reachability. So again, within the scope of the exam, you have to always remember that it's not a best practices exam. You don't have to optimize the network. You only have to solve it based on the questions that they're asking you. So if they just say, get full reachability, you can do it however you want. Okay, if they didn't say, don't use static routes, just put static routes everywhere. It'll solve the problem natively. But you'll see most likely, in general, there are going to be some restrictions of things you can or cannot do, because that's what makes the topology more difficult in order to meet the requirements within those particular restraints. Now, there are some other possible solutions to this that are probably better solutions from a design point of view. What are some of the other ways that we could prevent router 3 from advertising either a bad metric, or that we could prevent router 3 from even advertising the route to begin with? So again, think about it this way. When the route is coming from router 9, this is the only possible way to get to this advertisement. So this means that the advertisement should only be sent in this direction if we were to consider router 9 to be the top of the tree for this destination and everyone else is downstream. It makes no sense that anyone would send an upstream advertisement for the prefix. That's what router 3 is trying to do. It's advertising upstream reachability to a destination that's really downstream from it. So in other words, router 3 should not be redistributing what router 1 redistributed into OSPF to begin with. Now, there's a number of different ways that we can prevent it from doing this. We could simply say match the prefix and then don't advertise it. We could say set a tag value and then based on the tag value don't advertise it. We could say don't install it in the OSPF rib, which means if it's not in the routing table, you won't be able to do the redistribution. So there's a lot of ways to solve the problem. It just depends on, most of the time, it's going to depend on even finding the issue to begin with. Once we found it, then we can figure out what's the easiest solution in order to follow. So what I would personally do in this case is to do tagging. Tagging is going to be a more elegant solution here because it will always account for all prefixes later as opposed to accounting for them individually. Now, the way specifically that the tag works is that we're going to set the tag when we're doing the redistribution. So on router 1, we're going to do just a minor change under the routing process. So let's get out of the TCL shell on everybody. TCL quit. And let's say show run section router. So on router 1, we're redistributing OSPF into EIGRP. We're not setting any other attributes. Okay, what we're now going to do is create a route map. This is specifically on router 1 there. So we're going to create a route map that says set the tag. By default, the route map is permit. So I could have just said route map set tag, and we're going to say set tag 1. Okay, just for router 1, some simple value. Technically, the value itself is arbitrary. You can use whatever you want. It's just that on the other side, we need to make sure to match this same value. So we're setting the tag to 1, and we're going to say under OSPF, when we do the redistribution of EIGRP into OSPF, use this route map set tag. Now, the end result of this should be if we were to look now in the OSPF database, and let me do the undebug on everybody else. And let's look at the show IP OSPF database. we should now see for those particular routes, there was a tag value of 1 that router 1, who is the, again, ASBR, is originating. So these tagged routes, they go from 1 to 5. 5 refloods the LSA, it goes to router 3. On router 3, we want to tell it to not redistribute those routes that came from the EIGRP process to begin with. Now, we do want to continue to advertise the native OSPF routes, because in order to get to router 5, in order to get to router 10, the only option is to go into OSPF. But the issue is we don't want to feed back the routes that came from the source protocol to begin with. And that's the whole point of the tag. Now, we'll see in other certain designs, like if this was an MPLS L3 VPN PE to CE design, this would happen automatically, because the protocols now have built-in loop prevention mechanisms to prevent this. Because there is never, again, there is never a valid case in this particular design for the route to go this way and then come back, because 3 cannot reach it without going through this box. And again, this is the big problem with redistribution, that you cannot set general rules, because it always depends on what does this particular topology look like. There might be cases where you could send the packet to 3 and it could get there eventually, but this is not one of those cases. So again, we need to first start by visually looking at the topology, mapping out where the route advertisement is specifically going to go, where it should go, where it is actually going, and then the difference between that, that's going to tell us what the problem is. So now on router 3, if we look at the show IP route for 150.199, we see that we have it installed through OSPF, and it has a tag value of 1. This is the one that router 1 was setting. Now, essentially on router 3, what we're going to use is a reverse logic. We're going to say we're going from OSPF to EIGRP, and we want to say if the tag is not equal to 1, then redistribute. Else, drop. So in other words, only routes that do not have a tag of 1 should be permitted. Now, which particular logic you use, it's up to you. You can use the deny and then the permit, or you could use the permit and the deny. It depends on what particular attribute that we're trying to match. It also depends on the platform. Like in the case of iOS XR, they have a much better way to deal with this. They call it the routing policy language. In iOS, it's a little bit more strict with the route maps, and it's a little bit less flexible. So the way that we specifically have to implement this is by denying the tag and then permitting everything else. But the if-else logic is still exactly the same. We're saying if the tag is equal to 1, then drop, else permit. So on router 3 specifically to do that, we're going to say route map match tag. Match tag is going to say deny. That if we match the tag of 1, we are not allowing the route to go from OSPF back to EIGRP. Now that we have our explicit deny, we also need an explicit permit to allow the other routes. So we'll say route map match tag permit 20. Okay, we could match other things if we wanted to here, but we don't necessarily have to. Okay, now if we show run section, router. Let's go under EIGRP, and we're not going to give it this bad metric anymore. We're going to give it a normal type metric. So we'll say redistribute OSPF1 with a metric of, let's say 100,000 for bandwidth, 10 for the delay, 100% reliable, 1% loaded, 1500 MTU. But the key is that we're going to use the route map that is going to be called a match tag. Next, if we were to go to router 7, who again 7 was the one that had the problem to begin with, let's now look at the EIGRP topology. That if we show IP EIGRP topology for 151.99/32, the key change should be that 7 should not be learning the route from 3. So now in this case, since we only have one potential path, there's never going to be a loop. But for the alternate OSPF routes, we should be able to go through router 3 to get there. So for example, on router 7, if we were to say, how do we get to router 10, those routes should be routable via 3. because 3 is only saying to deny tag 1. These routes did not have a tag of 1, hence they are allowed, and then the end result is that we have reachability. But again, this type of principle, there are all sorts of different ways to implement it. We could match an access list that is calling the address of the prefix. We could match an extended ACL that's matching both the address and the prefix and the prefix length. We could call a prefix list, which would be a little bit easier because it just says 150.199/32. We would deny that. Then we could apply that as a distribute list in the EdgeRP. We could apply it as a route map filter when we're actually doing the redistribution. Another option, which would be a little bit more kind of a roundabout solution, would be to say to router 3, don't install routes in the rib that have the particular tag value. So here, instead of saying don't do the redistribution, we would implicitly tell it you're not allowed to do the redistribution by removing the routes from the routing table. Now, this type of solution might be valid if they tell you you need to route this way in order to get there. Because remember, as we look from router 3 now and trace to the destination, we're kind of going the long way around. And we're going to, so let's say from our loopback, we're going to 5 to 1 to 6 to 7 to 9. So specifically, the packets are going that way. But maybe we don't want to go that way. Maybe we want to go this direction, but at the same time advertise reachability to the other OSPF routes. The way we could do that is like this. If we show, first off, let me get rid of the redistribution. Okay, so we're not doing any redistribution, no redistribute OSPF1. And let's look at the prefix. The prefix is 150.199. Okay, we see that we're installing it as OSPF. We're installing it as OSPF through 5, but the originator is 1. So 1 is the ASBR that we're routing towards. Okay, we can also see that the route has a tag. The tag was set by router 1 when we redistributed EdgeRP into OSPF. When we are now trying to redistribute OSPF back into EdgeRP, remember what the condition is. The condition is not that the route is in the OSPF database, it's that it has to be in the routing table. So what if we removed it from the routing table? Well, one way we could do that in OSPF would be just to apply a distribute list to the route. So for example, we could say access list 1 deny 150.199, access list 1 permit any. Under OSPF, distribute list 1 in. If we now look at the routing table, we should see that the route is no longer installed in the rib as OSPF, which then means that we cannot redistribute it into OSPF. So from router 3's perspective, if we now trace 150.199, now we go through EdgeRP. However, in this case, since router 3 is on the edge of the network, nobody else should be impacted. So router 10, for example, should still be able to route the packets to 5, and then 5 would send them to 1. Now, where this really could become an issue is that if router 3 is transit for other routers to this destination. Because remember, in OSPF, when you filter the route from the rib, it doesn't mean you filtered from the database. And anytime that you're installing a different route than you are advertising, this is when you can have a loop condition. So if I say to you, you can use me to get to the destination, but then I'm routing through somebody else who is going through you, how would we know that? Okay, that's the issue with redistribution, is that we lose that visibility when we cross the boundary between the two protocols. Now, in this very specific case, it's not an issue, but in other cases, it might be. So the solution that you choose, it's not really a standard one that you say you always use tags in this situation, you always use a distribute list in this situation. It depends on how was the loop caused to begin with. Was it a data plane loop or was it a control plane loop? Was it a loop based on distance or was it a loop based on metric? In this case, it was not a control plane loop. The network was stable. So nothing was changing in the routing table, it's just that the routing table was wrong. So then in order to make it do the correct decision, we need to influence the attributes or we need to filter out the route. But in not all cases, that is actually going to help. So there's a number of other ways to do this. Like on router 3, we could say this. If we show route map, we have the match tag route map that says if the tag is 1, deny it, and then anything else is permitted. If we show run, actually let's say show IP OSPF database, and we look at these other routes that have a tag of 1. Okay, let's take 151.77 for example. If we show IP route 151.77, we see that is installed right now through eEdgeRP because this is an internal route. In this particular case, the default administrative distance of eEdgeRP is preventing the loop case. Because since eEdgeRP is lower than OSPF, the OSPF route never gets to the routing table, which means it can't be redistributed. But we could cause this exact same case if we were to go to this router, which in this case is router 7, and if we were to say, don't advertise your loopback natively into eEdgeRP, let's use redistribution. And we'll advertise it as an external route. So let's say, for example, on 7, let's say show run section eEdgeRP. And we're going to do this. We're going to create interface loopback 7 with an IP address of 7777. And then under eEdgeRP 100, we're going to say simply redistribute connected. If we now look at router 1 and show IP route 7777, we learn this through eEdgeRP, and then we're redistributing it into OSPF. The route loops back around to router 3. Router 3 should now install this as an OSPF route because OSPF's distance is lower than eEdgeRP. If we now go to trace to the destination, we should have another loop condition. Well, in this case, the destination is actually on 7, so it's not a loop. But if the destination was behind 7, if it was somewhere down here, then it would be. But from router 3's perspective, let's look at this. If we look at the show IP eEdgeRP topology for 7777/32, it says that the feasible distance right now is infinite. The reason why is because we're not installing the route in the routing table. But what we actually should see here also is we should be doing the redistribution. Let's say show run section router. Oh, the redistribution I took off. So let's say this, router eEdgeRP 100, redistribute OSPF 1, and then whatever the metric was. And if we look at the topology, okay, now we are originating it. We are originating it as redistribution. And we can see originating router is 3. Also, it says that the administrative tag is 1. Okay, that's what got copied from OSPF. So let's look at this in a little bit different implementation. Previously, I filtered out the route with a distribute list that was saying match the individual route 151.99. That was denied, and everything else was permitted. The issue with this implementation, though, is I would have to account for every new prefix that was potentially introduced into the network later. So it technically works, but it's a bad design. Because why would you, in a real deployment, want to have to maintain this list every time you want to add a new section to the topology? You wouldn't. And at some point, it's probably going to get out of administrative control, and then that's when you end up in the failure situation in the network. Because you have this on maybe multiple routers, it's only a locally significant value. So you'd have to make sure that it is enforced on every single point. So with the tagging, it's probably a little bit better because that's more of a general case. But there's another way that you can apply the tag as opposed to just through redistribution. We could also say this. We could say distribute list route map, drop the tag inbound, where if we show route map, this says if the tag is 1, deny. If the tag is anything else, permit, which now means if we show IP route 7777, we can no longer install it as OSPF, which means we can't redistribute it, which means we cannot create a loop condition. But ultimately, the end result is the same. The end result is that we need to stop router 3 from feeding the route back to the source protocol. And again, tons of different ways to do this. We could apply a distribute list out in eIGRP. Here we applied the distribute list in to the OSPF rib. We could say when we're redistributing between the two, match the tag and deny it. We could match the prefix and deny it. We could set the metric to be a high value here. We could set the metric to be a low value here in order to force router 7 to choose this over that path. We could go to router 7 and set the delay of this interface to a real high value, which means that we would always prefer to go that direction. So if you think about this within the scope of the lab exam, they're not going to grade you based on your configuration. There's too many variables. They're going to have to grade you based on the result. So that means that when you do the test, you will be able to tell, did I get this right or wrong? Because if router 10 can't reach the destination, that's the only condition. That reachability is not there, so you don't get the credit for whatever the question is. Now, unless they were very, very specific in the question, it would be an issue. So if they said, solve this without using route tags, without using the distribute list, without using an access list, without using this and that, but at that point, there's too many things to account for, so they're not going to grade it that way. They're going to look at what's the end result, does it work, yes or no? If yes, then you got it right. Okay, maybe if they add some conditions as well, like solve the problem but don't use a route tag, they would first say, is reachability there? Yes, that's the first condition. The next condition, did you use a tag? So look at the configuration, is the tag in there? If yes, then the question is wrong. So again, you have to think about what is this logic here that you would use if you were grading it, because from the proctor's point of view, they don't want to have to spend 5 hours grading your exam. They want to spend 5 minutes doing it. So from a practical point of view, they don't have the time to look at all of these cases. They want to group them together and what's going to be a simple test that I can run to see whether this actually worked or not. And in the case of redistribution, that's just going to be a reachability test. Okay, somebody else had a comment here, change the IP address. That's actually a perfectly valid solution. We could say on router 3, when we redistribute from OSPF into eIGRP, let's summarize, so that we give them a shorter match to the destination and they would choose the longer match. So we could go to the link level and say, give them a /31. They already had a /32 on an alternate path. They're going to follow the 32, and that's not the loop condition. So all sorts of different ways in order to solve this, but the underlying problem is the same. That the problem is that this is a metric-based loop because router 3 is feeding the route back to the source protocol, and it should never have done this to begin with. One other thing we could do, as someone else had mentioned, set the administrative distance. That works too. So we could say on OSPF, set the distance to be high for the external routes. Set it to be 171, which would have what result on router 3? Let's take a look at that solution. So on router 3, we're going to say show run section router. Let's get rid of the distribute list. Okay, this solution here, I would personally not choose this because this is a very dangerous thing to do in OSPF, that you are advertising the route but not actually using it. It's very easy to cause a loop with OSPF when you do this. You would be better off saying filter out the advertisement, which you cannot do in the OSPF database, but you can do when you're moving it between protocols. Okay, the other way here is the distance. It's basically doing the same thing. So if we were to say under OSPF1, the distance is for OSPF of intra area is 110. For inter area, we could say whatever. We could change this separately. So let's say 113. And external is 171. So in this case, the externals would be less preferred than eIGRP. And if we now show IP route OSPF, notice what we don't have installed. We don't have those external OSPF routes installed. But at the same time, if we were to now go to the connected link from 3 to 5, or from 3 to 7, and if we were to shut this down, then we should install those routes because that's our only possible path then. So if we now show IP route OSPF, now we do install those routes, but notice what's different. Now they have the higher distance. Now, again, the administrative distance is only locally significant, so this is kind of another dangerous solution where you would probably be better off using the tag value, because the tag you can apply in general to all prefixes without having to say this specific route has a higher distance or this specific route is filtered when I advertise it out the interface. It just really depends on probably what is going to be the quickest solution. So this might be, within the scope of the exam, this is a very easy solution to implement because it's only one command. We just say under the routing process that OSPF external is less preferred than EHRP external, which means we cannot install the route in the routing table, which means we cannot perform the redistribution.